I don't know what is it about today where everybody got some. Anyway, it's too bad. This is a lecture where you get I think of this, you get really exciting stuff in this one. This is a completely bizarro, weirdo, different way to think about the world. So let me anyway, I want to advertise this. Too bad. Anyway, I hope people will show up a bit later. But anyway, let's get started. So what I want to do is I'll start by going over what I did last time and tell you a bit about I told you about Clifford algebras. So let me just kind of summarize what I told you about Clifford algebras last time. Okay. Okay. So what? So the definition I gave of a Clifford algebra last time. So it started off as kind of as this very kind of concrete thing, that it's the thing that has generators. There's gamma I, gamma j, for j is equal to 1 up to n. There's n of them, and we've got and gamma, and they satisfy the relations that the anti-commutator gamma j and gamma k, which I write this way, is twice delta jk, times 1. So you've got an algebra that you've got n of these generators and 1, and then you could start multiplying these things together, but then they're going to satisfy these relations. Okay. And now what I also showed last time is that a more abstract way of thinking about this is that this is an algebra that's attached to a vector space V, which has a non-degenerate symmetric bilinear form. So this may be, the standard example would be like a real vector space with a standard kind of inner product on it. But you can have any kind of anti-symmetric, symmetric non-degenerate bilinear form. And then, okay. And for now, let's so you can always complexify this, but the basic example we're going to think about this is real. So this is a real vector space. And then what I showed was that what you could do is identify vectors with Clifford algebra elements by taking the components V is equal to, let's call this V1 gamma 1 Vn gamma n. So you just take the components of V and multiply them by the gamma matrices, and you'll sometimes also write this as V slash. This is the Feynman slash notation. So what you've done is you've identified the elements of the vector space with Clifford algebra elements, and so but they're sitting inside a certain kind of subspace of the of the thing spanned by the generators of the Clifford algebra. Oh, sorry, yeah, okay. And then what you can do, and instead of having these kind of relations, which you can think of as being the relations on which you get for when these things are an orthonormal basis vectors. Well, you can then, the relations are, well, one way of, actually the simplest way of saying it is actually that now you can multiply V by itself, and if you multiply V by itself, you're going to get just 1, and then with a number in front of it, which is the size of the vector. So the square of an element of the anyway, so now you can take vectors and start multiplying them, and if you multiply a vector by itself, which is something you can't do in a normal vector space, but but it's given by just the square of its size. And this is you can also write this more generally as you could get the same thing by using this for if you put v plus w in here, but then you'll get that this is a v slash w slash plus w slash v slash is equal to twice the inner product, or if you like, this bilinear form on these guys. So multiplying these guys knows about inner products, but all of this really comes down to kind of this kind of simple relation. And then this is just the kind of, you know, this is just kind of this written out in terms of a basis. Okay, and then what I did, this the slightly thing that I didn't go quite through the full argument last time, but I started doing some geometry. So one relation to geometry is that if what was it? That if you so if you have this picture, so if you have a vector w in any dimension, and then you have another vector v vector, and you want to reflect v vector with respect to w vector. So what this means is there's some hyperplane which is perpendicular to v vector, this guy, and then there's a notion of orthogonal reflection in that hyperplane, and that's going to take this guy down to here. So this is the anyway. So this is the vector reflected with this kind of orthogonal reflection with respect to w vector. And if you look at do some simple geometry, find the formula for this, and rewrite everything in terms using this identification. So writing all these vectors in terms of Clifford algebra elements, what you find is that v prime slash is minus w slash v slash w slash inverse. Okay, so it's reflection is given by conjugation, with a weird minus sign here. Watch out. And then now so then you're often interested in the fact that rotations. Okay, anyway, I guess we'll stop with this. But then what we're typically interested in doing is not in reflections of things, but in rotating things. And the idea is that rotation here. So we can get any rotation from an even number of reflections. Anyways, this is kind of a fact about geometry in any dimensions. And then so what that means is that you can get it. You're going to get it from conjugation, so this is conjugation by an even number of generators. In other words, so you have to pick some even number of vectors and multiply them together, and so you've got some kind of element of the Clifford algebra which is even in the sense of coming from an even number of generators, and then you conjugate by it, and you get any rotation. And but then you can realize that what you've done is you constructed these even numbers of products of these guys, and so you can make a group out of such things. And and the group of I said it a little bit more precisely last time. Let me say it a little bit less precisely today. The group generated by even number of W slash, and to keep track anyway, to keep things simple, you can just work with things that have the same work with unit length things, so you don't have to worry about keeping track of how the effect of the sizes of these guys. It's called spin event. And so and this you can see and this so this thing kind of acts, so spin of n acts on Rn by conjugating it. And what it's going to do, and there are going to be two different elements in here. And doing that is going to take the vectors in Rn and rotate them somehow. And there are going to be two elements in here that give you the same rotation. If you just put if you add a minus sign to one of these guys, you'll get another thing which does the same rotation. And this, so this is the spin double cover of SON. You've constructed that. Okay. So I think that was the and notice this that so what you've done is you constructed spin as you constructed it as a subgroup of this guy. And so this guy's not a group. This guy's just an algebra. This guy's got like 0 in it. But here, everything these are invertible elements. They live inside here. And since you can realize these algebras as matrix algebras of various sizes, then you've actually constructed the spin group as a matrix group. Okay. And so in low dimensions for spin 3, spin 4, spin 5, and even spin 6. There's those matrices that make up this group can be characterized in various ways. But for arbitrary n, there's really kind of no. This is really kind of the simplest characterization of what how to construct these groups. There isn't really anything simpler there. They're matrices, but kind of saying what kind of matrices they are is kind of tricky. Other than but this is the most straightforward thing. Okay, so that's the spin group. Okay, so this is pretty much, I think, where I stopped yesterday. And now I want to do something, give you a different way of thinking about it. So this is a very nice way of thinking about what happens at the level of the group. But you're often interested in the Lie algebra. And so at the level of the Lie algebra, let me give you, see what happens. So at the level of the algebra, so we want to study what the Lie algebra of spin of n is, and it has to be so we know we want the Lie algebra of spin of n to be the same thing as the Lie algebra of SON. Remember these groups at the they're kind of near the identity. They look the same. They have these have the same Lie algebra. It's only this guy has this. This guy is kind of a double cover of this group is a double cover of this group. But as far as what's happening on the tangent space of the identity, it's the same. It's the same Lie algebra. So remember the Lie algebra of SU for n is equal to 3. The Lie algebra of SU2 was the Lie algebra of SO3. So and here we know Lie SON as a basis of the epsilon jk. So I've written j less than k. Less than k. And this is the matrix that I could have at the j k slot. Now I've got a -1 here, and then a +1 here, and then everybody else is 0. So the J, the only entries that are here are J, K, and Kj, where J is less than K. Those are the only non-zero entries, and so these are just kind of the elementary antisymmetric matrices. We know that these guys are all antisymmetric matrices, and you can write any antisymmetric matrix as a linear combination of these things. And then what these do is these are the generators of rotations in the JK plane. And so then you have that so epsilon, then e to the theta epsilon JK is rotation by theta in the JK plane. So this is the general story about orthogonal groups, that you can think of them as any element is corresponding to a bunch of being given by some sequence of rotations in various planes. And if you want to write the rotation in a plane given by coordinates, by these coordinates in J and K, then you just exponentiate that guy, and you'll get some cosines and sines in various places. Okay, and then now so the question is really kind of what. So we know. So we want the Lie algebra to spin in to be some things which you can kind of exponentiate them and end up here in spin in, and we want them to we want to find out what corresponds to the epsilon JK basis on this side. And so what we're going to do is use this fact that if you take gamma J, gamma K, and square it, what you're going to get is, well, it's good to do. So it's gamma J, gamma K, gamma J, gamma K. But now if you take and we'll see, anyway. So if J is, and we're going to assume that J is different than K. So this is a J not equal to K. Now if I take I can use the anti-commutation relations to interchange the K and J here and get a minus sign. So this is minus gamma J, gamma K, gamma K, gamma J, right? But now these guys, if you multiply them by themselves, you get you get 1. And so gamma K is equal to 1, and then you get 1 here, and then the gamma J is equal to 1. So this is equal to minus 1. Okay. So these guys are going to be things that if you square them, you get minus the identity, and you get minus 1. You get minus. And so, and what this implies is that if you take these guys and exponentiate them, and then use the use the standard series expansion for the exponential, you're going to get 1. Actually, let me not write this out, but it's anyway. Just write out the exponent, write out the series expansion here, and and then they use the fact that this guy, when you square it, you get minus 1, and then what you're going to find out is that you get the oh, sorry. Okay, sorry. I'm going to need. Let me do it. I'm going to need this guy to make this next calculation work out right. I'm going to have to put a 2 here, if you like. And then what you're going to find is that this is cosine theta over 2 times 1. So when you expand this thing out, you're going to get a bunch of ones with some coefficients. And the coefficients are going to be the cosine of theta over 2. And then you're also going to get a gamma j, gamma k times the sine of theta over 2. Anyway, so if you just expand this exponential out, you'll quickly see that this is going to be true. Okay. Now, so now what happens? So the claim, as you can show, the claim is that conjugation by this guy is going to be is that this is really the well, anyway, the claim is going to be that these gamma is well, let's work. I guess better say what I get here. So conjugating meaning b slash by e to the theta over 2 gamma j gamma k. So I want to take a vector but thought of as a thing in the Clifford algebra, and I want to kind of conjugate by this guy, and then see what because the claim is going to be that these are elements of the spin group, and conjugation by these guys is going to rotate these vectors. So we got to check and see if that works. To check to see if that works, you do well, what you show is that the you show one that conjugation by, well, let's do it this way. So then e to the gamma j gamma k gamma l e to the k is equal to if L is not equal J or K. Okay, so if L is not equal to J or K, then you can use it anti-commutes with the gamma J and gamma K, and if you and you can then you can then use a series expansion for one of these guys to the exponential to see that you can just move this over here and it and nothing happens. So the what this guy does, if you take something which is not in the JK direction, which is in some orthogonal direction, it's gonna leave it alone. So that's good if it's a rotation. And then what you have to show that if you take e to the minus, if you conjugate something that's in the JK plane. So that's going to be something, say Vj gamma j plus Vk gamma k. So if you conjugate something which is some linear combination of the basis vectors in the JK plane, what it's going to do is it's going to give you you're going to get, well, and this isn't too hard to work out, but anyway, the answer is just you get Vj cosine theta minus Vk sine theta gamma j plus Vj sine theta plus Vk cosine theta. And these coefficients are exactly what you get by a rotation by theta in the JK plane. This is exactly the rotation of the coordinates you expect. And so in general, generator. So what happens if I take one way of writing this is that if I take e to the minus theta over 2 gamma j gamma k, and take and then conjugate an arbitrary vector, what I'm going to get is I'm going to get the same thing I would get if I rotated the vector, and then I took the Dirac slash of it. Okay, and I think sometimes it's better to use. Sometimes I'll use the notation. Also, another notation would be I've often called this gamma of v vector, and this would be gamma of e to the theta epsilon j k. So sometimes I'm using this notation that gamma of a vector is the Feynman. What I've also written is the Feynman slash. Okay, and so then if you then if you differentiate this relation with respect to theta, you get a so taking d d theta at theta is equal to 0, you get the infinitesimal version of this, which is a commutator relation, which is that 1/2 minus 1/2 gamma j gamma k, and then gamma of v vector is gamma of epsilon jk. And so what this is saying really is that these guys. So anyway, so these guys play exactly the same role as epsilon jk. And I guess I should say this. Maybe let me write it up here. So the SON is the same thing as the spin of n. And what's here, the epsilon jk, I hope I've got this, I've got all this right. It should be minus 1/2 gamma j gamma k. Hope I've got these. It's hard to keep track of these signs. Yeah. And there's an alternate kind of way of thinking about this. Alternatively, to show, compute commutators of that's a 1/2 gamma j gamma k. For j less than for each choice of j less than k, and you get the same relations. As for commutators of the epsilon jk. So if you just take two values of j and k and take the corresponding commutator of these guys, you're going to get something, and it's going to be the same thing you took if you took this matrix for j and k and took its commutator with the matrix for some other indices j and k, and then you get some string of things, and that's exactly that. So that's exactly gives you the Lie algebra relations on a basis here are the same as the algebra relations on a basis here, just in terms of commutators. So this is another way of showing but I think this other way of showing that these quadratic things in the gammas, they really do explicitly they are the infinitesimal generators of rotations. Okay. Okay, so maybe stop that. Yeah, so that's I think what I want to say about that. Maybe so are they? So I think I'll stop at this, and we'll come back and see this again. But this is the first pass at showing that now that the Clifford algebra allows us to get our hands explicitly on the not only on the spin double cover of the SO group, but also on the Lie algebra. And I think I should say that these calculations I did here, these were all for the case that these were all for R is equal to N, S is equal to 0. So these were all for the positive. The calculations I did were for the positive definite case. But essentially the same calculations also go through for any for any signature here for non-zero S, if you like. But you just have to. There's some more signs to keep track of if you do that. Okay. Ready? Just have any questions about this? Because now I want to go on to something else. Okay. So now the next thing I want to do is kind of go, in some sense, what I'm doing here, in the normal way when you talk about quantization, you talk about the the phase space and functions of the phase space, and then you do classical mechanics with Poisson bracket, and then you quantize and get these P and Q operators, and you get your acting on your quantum space. So what I've done, the way I've been doing things here, it's kind of a bit backwards. So we started with a fermionic quantum system, the fermionic harmonic oscillator, quantum harmonic oscillator. So now what I want to do is I want to go backwards and claim that there really is a way, that there is a fermionic analog of Hamiltonian mechanics, of everything we did in Hamiltonian mechanics. And so that's the thing I want to do today, main thing. And this is what's sometimes called pseudo-classical mechanics. What this so what this is going to be is we're going to try and redo the story of phase space and polynomial functions on it and their Poisson bracket with a but we're going to replace the Poisson bracket. Instead of it being this anti-symmetric thing, it's going to be something that's anti-symmetric on the generator. It's just going to be something that's symmetric on the generators. And so let's see how much. So there's a whole. Okay. So what we want is so what we want is a fermionic analog of polynomial functions on the phase space M. Okay. And so in the bosonic, this was in the bosonic case, what you did is you took M is the dual, and then polynomial functions on M are given the space of such thing is actually the same as the space of taking all possible tensor products of these guys and taking the symmetric piece. So polynomial functions on M is S star and V star. So what it is you're taking V star, taking all. Well, you're taking the sum over all k of k of these, and then you're taking well, it's a subset of all of these, but it's the symmetric ones. Okay, so the things that are so for these to behave like polynomials, they have to not. You can identify them with tensor products, but they have to be symmetric tensor products. anyway, this is the kind of abstract. The reason for thinking in terms of this abstract nonsense is we'll instead. So we'll instead make the anti-symmetric. So-called lambda star. Okay. So what we're going to do is we're going to take, and this is actually, and what we're going to do actually doesn't actually require that you start with an even dimensional subspace. But you can start with an even-dimensional vector space. You can start with V. Sorry, and here this was M. So this is S star M star. But we're going to do this for any, and this is for any vector space V. Now it turns out if you want to start manipulating these gadgets, it's probably it's a good idea. It's also the same thing you do when you do polynomials. If you want to write down polynomials, what you want to do is you want to write them down in terms of in terms of products of the coordinate functions with respect to a basis. So you want to write down your polynomial and variables. You want to write down in terms of the coordinates to multiplied by themselves to various powers. So if you want to kind of actually work with this guy, you want to work with them with respect to a basis. So let's choosing a basis. A basis EI of V, EJ of V. Okay. Then we're gonna take coordinates to be. Let me do the psi j. Psi j, and these are an element of the dual, and so and these are just like your normal coordinates, except that now if we want to work with start taking the tensor product of a bunch of these guys and not work with the symmetric part but work with the anti-symmetric part, then we can write down elements of that anti-symmetric tensor product in terms of these guys, but we just have to be careful that when we multiply two generators, we have to put in, it depends which sign we multiply them. So to get the anti-symmetry in the tensor product, we're going to have to take care of what, if we multiply a bunch of these together, what's the ordering, and that's going to be important. So what you have is you just have that just have the relations, and then this V star is the algebra generated by 1 AJ and satisfying, and just that the J K is equal to, well, plus K J is equal to 0. Okay. So in other words, what I mean is that this guy, so when you interchange two indices, you pick up a minus sign. And in particular, this implies that A squared is equal to 0. So if we try and work with these fermionic polynomials, so what these really are is kind of elements of this space. They're just going to be, it's going to be like normal polynomials, except the problem is you have to when you multiply two things, if you're multiplying, if you see something multiplied by itself, it just gets killed at 0. And if you multiply two things for two different values, you have to take care of the order, and you're gonna, if you interchange two things, you're gonna pick up a sign. Okay, so that's the rule of this thing. And so more explicitly, so you get a basis. Well, anyway, maybe you could say so. This has a basis. Each one has a basis. So one that say to J, say to K, K less than K, etc. up to say to 1, A to 1, multiplied all the way up to A to N. And so this is going to be it has dimension 2 to the n. And if you want, these can be real valued functions, they can be complex valued functions. But anyway, in either case, with this is what a basis looks like, and it's dimension 2 to the n. You'll see it's somewhat similar to the Clifford algebra. So to give things away, the Clifford algebra is going to be the quantization of this guy. But this is what it is. And so these things. So people like to kind of talk about these things and say, well, this is you're doing a new kind of geometry. You're doing supergeometry where you've got these fermionic coordinates as well as bosonic coordinates. But the problem is that these there's something very funny about thinking about it as geometry. It's only geometry in a very abstract sense, because there's no, if you have some kind of fermionics, if you try to think of a fermionic space, there's really no such thing as a point in the fermionic space, because if you have an algebra of polynomials, what a point is what you get is something that to every polynomial you associate a number, which is the value of the polynomial at that number. Well, there isn't any way of associating points to these guys. So it's kind of it's a geometry without points. There's some kind of very, very vague way in which you can think of it as being, if you're at a point in a space and you want to just understand the infinitesimal geometry, so your geometry only has kind of one point, and you want to understand the kind of infinitesimal geometry, then there's a sense in which you can think about this is telling you about that. And maybe one other thing to say, very general, is that if you've studied, so sometimes you write the product. You write product. So to make clear that this is a product in this antisymmetric exterior algebra, you write it as let's see, J wedge. Okay. So sometimes you talk about the wedge product, and this is a giveaway that this is an antisymmetric product, but it's the same product that I'm implicitly using here. And so sometimes you'll see this in differential geometry. Differential forms. So this is just a comment for anybody in case you've seen this or do see this at some point. The story of differential forms on a manifold. So differential forms are functions on a manifold that take values dual, yeah, do the dual. Yeah. So what you do is in in geometry, at every point in the manifold, there's a linear space, which is the tangent space. It has a dual. It has a dual. And if you're taking the anyway, you're doing exactly the same construction here, except in other words, this is the case where V is the tangent space at a point X, and then it depends. This kind of varies depending upon where you are in the manifold. And then, but then this guy is the standard. So coordinates. So then you have a basis of T X M star are the D. So they're often written this way. If you know that you have your coordinates in the space are x sub j's, then when you write d x sub j, you have a corresponding that this corresponds to. I mean, x sub j is a local coordinate, so locally it's kind of a basis for the duals to the tangent vectors. So putting the d in front of it says, well, you think of it as a basis of these guys, and then the product is, it's the product we've been talking about in here, and it's written as a wedge product. So when you see differential form calculations, you'll often see, things involving dxj wedge dxk. And they'll follow exactly the same rules I've been talking about here, that if j is equal to k, this guy is 0, wedging something with itself gives you 0. If j is not equal to k, then this is minus dxk. It's minus dxk wedge dxj. So anyway, this is just in case you either have run into or do run into the theory of differential forms. It's really kind of a somewhat a good thing to keep in mind here, that it's a somewhat more elaborate version of what I'm talking about, because what we're talking about is just a nice finite. These are just a nice finite dimensional. This is a nice. There's only a single vector space V we're talking about here, and then you have the story in differential geometry. You have a different tangent space at every point in the manifold, so you have a much more complicated story to talk about. Okay, so that's some background. What do I want to do? Okay, and I'm trying to think if I should. I'm not sure how much I actually use. I don't think I'm going to say the next part also very quickly, because I don't think I actually really use this very much. But it's good to know. There's an analog on the calculus for fermionic. And this is just that if you take you just define so you define the notion of derivative with respect to j, and what it is on some function. So if you got some function of the size, then what you do is you write it as well. Maybe I better let me say it this way. So if f is, let's call it fa, let's say it psi j fb. So fa a fb don't depend on psi j. So what you can do is you can find, I mean, the thing about these, you can always, up to a minus sign, move things around, move the order of things around. And the these fermionic polynomials, either if you pick a j, either they'll have a psi j in them or they won't. If they don't put the things that don't have a psi j here, and put the things that do have a psi j, make them in this form, put put this over to the left, then you define the f p psi j is fb. Okay. So differentiating this thing with respect to this variable is just going to give you this guy. and so you can define a derivative this way. And the only thing that's a little bit, anyway, it has a little bit funny characteristics. One thing is that if you take two derivatives, you're going to get 0. So there are no second, in this theory, there are no second derivatives, only first derivatives. And are no second derivatives in the same direction. You can take derivatives in one direction, then in another direction.
Are FA and FB just real numbers?
No, so they're functions. They're functions. So they're fermionic polynomials. They're elements of. I mean, they're elements really of what really you should think of as the anti. Or if you like, they're arbitrary combinations of these. They're arbitrary polynomials in these psi's, except that the multiplication is this antisymmetric multiplication. So I can call them fermionic polynomials, or you can think of them as these guys, whatever. Okay, and then anyway, and then you can figure out there's a you get I guess there's all sorts of fun stuff you can do here. Then there's a Leibniz rule, which says that if you differentiate with respect to j, a product of two of these fermionic polynomial functions, what you're going to get is you're going to get the j f times g, and then then you should, where you expect to get an f times g. Then you have to, so this is the usual Leibniz rule, but now you have to put a minus sign here, and then you put it to the order of f. And this is for f a monomial. So in other words, if in general these functions are linear combinations of monomials, but if f is a monomial, then this is what's going to happen. And so you get the normal Leibniz rule, except you have to be a bit careful about ordering of things, and there's minus signs to keep track of. And then there's similarly there's a notion of integration. And one way of saying what integration is that integration. So the integral.
Also, you assume here f is homogeneous. So did you assume here f is homogeneous?
Yeah. That it's all just 1 degree. So it's some. Not necessarily. I mean, homogeneous, I would think of as means that all things are the same degree. I mean, a monomial. I just mean something that it's so f is some number times anyway. Some say it's anyway. It's going to be some number times say psi j, psi j1, psi j2 to jk. I mean, so it's just going to be, it's just a monomial. It just got one kind of thing. And because the point is, you don't actually have powers of these guys, because if you have more than, if you have these guys get multiple, if you've got more than a single one of these things, then you're gonna get 0. Okay, so it's just a anyway. But I just need I guess it's right. Homogeneous might also work. Also, I mean, that will also work. I just need this thing to have a well-defined degree. I have to, and all I really need to be clear on is I need to be clear whether I'm talking about something that's odd or something that's even. Now, a general thing in here is not even or odd. It's something even plus something odd. Something can be written in terms of an even number generator. Something can be written in odd number generators. Well, all I'm saying here is that you have to here f has to be something that's either even or odd. And if you have something that has an even odd piece and an odd piece, you have to break it up and do it separately. Okay, then integration. I should. This is sometimes written D1 D, and this is just the coefficient in f of okay. So remember that. So this is going to have pieces of all sorts of different degrees, but there's a one-dimensional top degree piece, which is the thing that multiplies, this psi 1 multiplied up to psi n, and then just the coefficient in that function of this guy is what is the integral of the function. Anyway, I think let me not go further down this path because there's a whole long story of kind of how to work with all the rules of doing calculus in these fermionic variables, but it's not it's mostly not stuff we're going to use. We're doing something a bit different. So I just want to kind of indicate you can do this. Okay, but now, but what I really want to do though is what I'm really at is that I really want to do an analog of what I want to do with these functions. Is I want to think of them as analogs, as fermionic analogs of the observable functions, which are the functions on phase space of classical mechanics. So this is what our pseudo, and I'm going to try to put an analog of the Poisson bracket on these guys. So here. Okay, so recall. Let me just go back to this. So recall. Hamiltonian mechanics. What's the basic setup for Hamiltonian mechanics? Is you're going to have f is going to be, and let's just stick to polynomial functions. So let's just say f is some polynomial function on M. Okay, so it's going to be so it's a poly in generators Qj, Pj, and then you've got the Poisson bracket, which is the thing on generators. So anyway, it's the thing you define on the generators, like Qj, Pk is equal to delta Jk, and then for the Poisson bracket of two Q's is 0 and of two P's is 0. But you define that, and then this has the and then you extend this using the derivation property to any polynomials. So this has the property, the derivation property. F1, F3 is equal to F2, F3 plus F2, 3. Okay, and then you can. Using this, you can extend this from knowing what it's doing on generators, what it does on any polynomial. And then what you have is that and then you have a Hamiltonian. So then dynamics, what happens is given by the way functions change in observables change in time is given just by taking the plus-home bracket with some function h. So h is the Hamiltonian function. Okay. And one reason the plus-home bracket has to have this derivation property is so that, taking plus-home bracket with this, it behaves like a derivative. It has the same. If you do it to a product, it better obey the Leibniz rule. So that's quantum mechanics. So what we want to do is we want to change. So let's change to f fermionic f element of change. So M goes. We can take to be any vector space. Not doesn't have to be even dimensional anymore. And so now take F to be one of these fermionic polynomials I've just been talking to you about, and then define the on generators. What do I want to do? So I'm going to take on generators. Let's define the bracket on generators. Let me well, I want to say this. Oh, let's define this bracket on generators. Let's take I want to try to do. I'm trying to decide what level of generality to say this at. But anyway, let's just take the so that here let's go V W. So V W are element of V star. So these are just kind of order one things in here, things that you can write as some linear combination of the zeta of the psi j's. These guys. So anyway, so you figure out what this is, and then extend by so then you have to take a different you have a different Leibniz rule. Okay. I'm going to run out of space here. Okay, wait, let me. So extend to any fermionic polynomial. By to F2. So when you change the order, you're going to pick up a minus sign, but then there's going to be an extra minus sign, which depends upon whether these things are even or odd, and it's a minus sign is to F1, F2, and so F is equal to 0. These are the degrees of these things. I guess this is 0 if it's even, 1 if it's odd. Okay, so these things are going to be So on things which are order 1, which are odd, this is going to be minus times a -1 to the 1. so it's good. So on the generators, this is going to be symmetric. It's going to be it's the opposite of the Poisson bracket. But if you have even functions in here, if you have even things, then even is going to give you a 0 up here, and you'll get a minus sign here, and it'll behave like the Poisson bracket. So this will do the same thing as a Poisson bracket on even fermionic things. It'll have the opposite sign, the opposite symmetry on odd things. Anyway, and it's and then you have to the Leibniz rule, the correct version of the Leibniz rule then has to be F1, F2, F3. Is, you could take this, you could do this, do F3, but then you have to get but then the next part of it that looks like F1, F3, F2, you're going to get a minus to the F2, F3. Okay. Anyway, so you have you have a Leibniz rule, but with sign with sign problems. You have to, and which in some sense corresponds to if you do everything in terms of generators, you're just keeping track of how many generators you have to move past to get things in the right order. Okay, now then once you do that, now what the claim. Okay, so if you do all this, what you've managed to construct is you constructed an analog of the Poisson bracket, which has all of the it has all the properties to be a Lie bracket on even things, but it's got it's got not quite the right Lie bracket. It's got Lie bracket properties with some weird signs when there are odd things involved, and this is what's called so this guy is a well, okay, maybe I better say it this way. Maybe the better one. Yeah, okay. Let me go ahead with this. So let's define a super Lie algebra. Is a vector space V with some even basis elements, some odd. I'm not really saying this. Sorry, there's got to be. I'm not saying this very well. Let me see how this works out. But what you want to do, some are even, and basis elements maybe be better to say generators. Odd generators. And then it comes with a. So I'm going to write the. So if xy is a vector space, so xy, y are on V, are elements of V, but this vector space you may have some, it has some directions in which there are even directions, some directions which are odd directions, and you've got there's a Lie bracket on these things, plus or minus, and what it is it has this property that if it has this the symmetry property is that one. It's this thing. There's a minus. There's the usual minus sign, and then there's a minus to this thing to x y. So it's if these generators are kind of in the even direction, they're basis elements in the even directions, then you just get it's just the Lie bracket has its normal properties, and if they're in the odd directions, then instead of this being kind of a commutator, it's a anyway, you have anti-symmetry instead, you have symmetry instead of anti-symmetry. Okay. And then
we use the subscript plus or minus for the bracket.
Yeah, so the plus or minus here just means it's just the notation for I'm saying that so this bracket means it's a bracket in a not in a Lie algebra but a super Lie algebra, and the plus or minus is just telling you that there some things are going to be it's going to be a Lie bracket, it's going to be a usual Lie bracket sometimes, and it's going to be a and some of these things are going to be commuting, some of them are anti-commuting. So the plus or minus is just the notation saying, watch out. This is not in a Lie algebra. It's in a super Lie algebra. Okay. And then I think I better not try and write this out here, but you get a in the notations you have a so satisfying the super Jacobi identity. So the usual abstract definition of a Lie algebra is that it's really just a vector space where I've defined a bracket operation on the vector space, which is anti-symmetric and which satisfies the Jacobi identity. A super Lie algebra is the same thing, except your vector space can have even directions and odd directions, and it's and correspondingly you're going to have your bracket is going to have symmetry or anti-symmetry in those directions, and the Jacobi identity is going to have some funny signs to keep track of, which I'm not going to try and write down here. So this is just the abstract definition of what a super Lie algebra is. And so the idea of this is that if all of your if all the elements in V are actually even, there are no odd elements, then this is just the definition of a Lie algebra. It's just a Lie algebra. But in general, and if everything is odd, then you're going to have then you're still going to have a Lie algebra. So the problem what's happening here is that what we'd like to do is we're trying to find so we're trying to find an analog of what we did in the in the case of P's and Q's. And then for linear things, we found that since the Poisson bracket of P and Q was 1, we could say that the P's and Q's generated a Lie algebra, the Heisenberg Lie algebra. The problem that we're going to have here is that everything is going to go through, except the analog of the PQ is equal to 1 is going to be a anyway. I mean, the analog of the Lie bracket on P's and Q's is going to be this anti-symmetric, being this symmetric bracket, not an anti-symmetric one, and that's not going to give you a Lie algebra. It's going to give you a super Lie algebra structure. So the piece of the story where we talked about the Heisenberg Lie algebra, here it's going to be the corresponding thing is not a Lie algebra but a super Lie algebra. But otherwise the whole story is kind of going to go through. So let me kind of then just kind of finish up by kind of saying what the story is. Actually, maybe let me do that. Maybe let me do that next time, and let me better to finish by telling you about some of the physics about this to actually get to the pseudo-classical mechanics. So what we're going to do here. Classical mechanics. What we're going to do is we're going to have the observables. Let's say F is going to be one of these. it's just going to be one of these fermionic polynomials, and those are going to be observables, and the way they're going to change in time, f is going to be given by taking the f with h plus. So it's the same rule, except we're going to use this new kind of this kind of fermionic Poisson bracket instead of this guy. So this function can have an arbitrary degree. In order for this to look at all like standard mechanics, we want h to be even. Okay, and so h has to be you want, well, actually I shouldn't say that. Actually, it's also going to be interesting when h is not necessarily even. But let's just take h. Let's say that let's look at some examples where h is even. So I mean the simplest example to think about, I will leave you with that, is to take v as R3. And so v star has a basis psi 1, psi 2, psi 3. Okay. And then the functions as a basis 1, 2, 3, 1, 2, that's a 2, 1, 3, 2, 3, sorry, and okay. Sorry about my handwriting here, but this is okay. So there's one of these, there's three of these, there's three of these, and then there's one of these, and so this is dimension 8. So this is dimension 8. So the possible fermionic functions on this odd fermionic phase space are, the space of functions is a finite dimensional space of 8 dimensions, and here's a basis of it. Okay, and so if we want to have a Hamiltonian and have a behavior somewhat like usual behavior, we want our Hamiltonian to be even, and Hamiltonian and 1 is kind of uninteresting. So the general case is going to be some linear combination of these two guys. Okay, so what we're going to do is we're going to take h is equal to well, let me take it. Let me call it let's take it b1, so 1, say 2, 3 plus b2. 1. I may get the signs wrong in doing it this way, but 1, 2, okay. And so for some numbers b1, b2, and b3. So an arbitrary Hamiltonian is going to be given by these guys. And then what okay, actually now I realize I better. And then, so okay, so let me go back to this next time. And so next time we'll show that for if you put an arbitrary function here, that show that time dependence is theta t goes to is equal to 0 rotated by rotated by t in plane sorry, okay, I shouldn't. So I'm getting to the end of the blackboard and to the end of the story. well, what's so what'll let me finish working this out next time. But basically, what this is saying. So this is kind of the simplest possible analog of a pseudo-classical analog of mechanics. And what you're doing is you're starting with a your phase space V is not even dimensional. It's three-dimensional. But it's got a but this guy. So this guy J K. And what you're defining this to be, now I've got delta is delta JK. So this thing is that's right. Yeah. No, wait a minute. Yeah, plus. Yeah. Or now now I'm worried that I got my do I need the 2 there? I think I need the 2. No, I guess not. The 2 is hard to keep track of. But anyway, it's this. So it's this nice, and this thing is symmetric. This is just the standard. This guy is really just the standard inner product. This kind of fermionic version of Poisson bracket is just the usual inner product. And sorry, I've gotten to run out of time to do this. Probably I got to take this up next time. But if you ask, what's going to happen? What's going to happen to some kind of function of some kind of function in here as time evolves? Well, you see what it does in the generators, and the generator, if you have the basis elements at time 0, they just get rotated in the plane perpendicular to the vector given by the b's as you move along. And so this is kind of a anyway, it is what it is in terms of pseudo-classical mechanics. Maybe the reason for that's actually really interesting about this is that we're gonna, if you do exactly the same, so do exactly the same thing that we talked about in the bosonic case, where we had a Lie algebra of functions on phase space, and we looked for a unitary representation of that Lie algebra. Well, what we're going to add when we quantize here, what we're going to do is we're going to take this Lie algebra of functions, take this super Lie algebra of functions on this kind of pseudo-classical phase space, and asking for quantization, we're going to say, okay, these guys form a super Lie algebra. Now let's find a unitary representation of that super Lie algebra. And the unitary representation of that super Lie algebra is going to be exactly given by replacing all the gammas, all these zetas by corresponding gamma matrices. And these things, so these things are all going to end up just being given by essentially sigma, various kinds of sigma matrices. And your quantization is going to be your operators are just going to be 2x2 complex matrices acting on C2, and you're going to have just have found a completely different way of thinking about the the standard spin 1/2 kind of qubit simplest kind of quantum mechanical system. So sorry for I kind of didn't start off into this, and I need to develop some more things to work this out. I'm going to do that next time. But that's this is kind of the simplest example of pseudo-classical mechanics. It's just what it's really is doing, it's really just describing things that are it's describing the standard kind of rotation that you see about a magnetic field in the qubit case, and when you quantize it, it's exactly the qubit system. Okay, so sorry, I better stop there. So sorry for this getting too fast and too confused at the end. So I'll pick it up here next time. And what I want to I'll just kind of work out a bit, say something a bit more general about what this in the general case, what the structure of this problem is, the structure of this super Lie algebras that you get here, and what the relationship is to the whole story about spin-in that I was telling you at the beginning of the class. and then to end this part of the thing, we'll go back and look at the super analog of the harmonic oscillator, and we'll recover the fermionic oscillator that we started with. Okay, so that's the other example, is kind of the fermionic oscillator is the other example, and this is the other example, and then that'll be the pseudo-classical mechanics, and then we'll go on to say a bit more about, use all this stuff to kind of look a bit more at the structure of spinors, and see how it gets, because I've told you now about how to get spin groups in arbitrary dimensions, but I haven't told you very much about, what these groups act on, and how to think about the things they act on, which are the spinors. Okay. Okay, so sorry for the confusion here at the end, but any other questions right now?
So if these are, sorry, the sign or
yeah, there's sign.
Are exactly mapped after condensation mapped to the gamma matrices, then shouldn't the anti-commutator relation have the factor to them, because gamma matrices multiplied with side would be.
Well, you're going to have. Well, it is. So this plus is, yeah. I mean, it's the. I think I got this right. Yeah. I mean, I have to.
Like if we set j equals k.
Yeah. Yeah. So you have. So the thing which is confusing. Let me try and remember this. So the thing which is confusing. Yeah. Okay. And now I'm maybe it's let me not try to answer that right now, because I'm just going to answer it in a more confused way, and the whole plan for next time is to do it properly. So it's that. But yeah, I'm just kind of advertising. One reason to be interested in this is that you should be able to get the standard. But it's true that when you yeah, I mean. Remember, so what's going to happen is the psi's are going to go to gamma matrices, and the Poisson bracket is going to go to the Poisson bracket is going to go to an anti-commutator, and you should, if I do this right and if I get the coefficients right, you should get the Clifford algebra relations on the gamma matrices. And yeah, so the analog of the Heisenberg commutation relations of QP is 1. Yeah, that should, if I get these coefficients right, that should give you the same definition as the properties of the gammas for the Clifford matrix. Okay. Okay. And so the one thing that I kind of, and just to make clear, I mean, the thing that one thing which you're missing here was that in the in the bosonic case, you wrote down this kind of algebra of these P and Q operators, but then you also then kind of realized this algebra of these P and Q operators by acting on like a space of functions of just Q or something, or functions of P or functions of Q. So what I haven't here, I'm doing the pseudo-classical stuff, and then when I quantize, they're going to be things with operator relations. But the next part of the story is to kind of find the analog of what's the state space. In the bosonic case, the state space was just functions just of Q, or functions just of P, or functions of holomorphic things, not anti-holomorphic things. Here, you're going to have a similar question here. How do you construct the state space? How do you quantization is going to take these things to operators with some relations, but what's the space those operators act on? And that's the question of spinors, which I wanted to get to later. Okay. Okay. Any other questions?
Yeah, I get a question about, so just to make sure, for fermionic polynomials, if we're talking about monomials, then the degree can only be either 0 or 1. Right?
Yeah. Yeah. So everything. Yeah. So especially as far as these signs are concerned, these sign problems, it's always. Yeah. I mean, are you talking about when you write this thing out in terms of, well, it's always going to be some you can write these things out in terms that are given by multiplication of some number of generators. Is the number of generators even or odd? That's always what's going to determine the sign. Or if you're calculating, it often just comes down to just keeping track of the order, and then at various times you're going to have to do a calculation. You're going to have to interchange the order, and then you pick up a minus sign.
Okay. And so like then the differentiation on these fermionic polynomials, like because of the fact that if we differentiate it twice, it's just like the zero operator.
Yeah.
So then we could so like the entire theory of differential form, we could use that to construct like the chain compounds and everything like that.
Well, it comes up in that. Maybe, see, I mean, since you know about differential forms, let me just have to watch out that there's let me just tell you one thing. So in differential forms, there's this interesting operator, which is what you call D, and that in some sense is the sum over J of D xj, and then D xj a wedge. Yeah. Okay. So you're doing. You have to watch out. Why is the differential forms are much trickier, because differential forms are two pieces. They're kind of functions of x times multiplied by some dxj wedge. So there are some functions of all the there's some. They've got real infinite dimensional functions going on here. An infinite space of functions. I mean, an infinite dimensional space of functions here, and they've got these guys, which there's just kind of 2 to the n of these guys. So there's kind of 2 pieces of the differential form calculation. There's this, and what I'm telling you about here is all fundamental. It's all about this. It's all about this piece, and so this part of when you're trying to find the Durand differential in differential forms, you've got part of the story is just you're increasing the degree of 1 by wedging with a coordinate dxj, but there's also this piece. There's also a true derivative there. So the fact that d squared is 0, which is kind of the fundamental fact about differential forms, it has to, it's true. It has to do with the fact that it does have to do with the fact that the derivative, the appropriate derivative on these guys is squares to 0, but it also has to do with the fact that the when here you're taking that the difference between dxj, if you take mixed partial derivatives, they're the same, and you need that to be true also. So the D that you're going to see in the theory of differential forms is a more complicated object. It's got a more complicated story, and it's squaring 0 for a somewhat more complicated set of reasons. But it's partly true for the same kind of. You can rewrite this D in terms of this kind of bogus kind of derivative on this guy, on this piece of it. And the fact that derivative squares to 0 is going to be part of this calculation, but it's not the whole thing because of that help. Okay. And this story is actually interesting. This is kind of what I'll kind of end up with in a week or two. I want to this differential form story is actually a story where you're putting together. I'm telling you about this kind of part of the story now in this fermionic thing, and I told you about this part of the story in the bosonic thing. So really, if you want to kind of think about, if you want to think about the theory of differential forms as kind of a quantization of something, it's going to be a mixture of your state space is going to have part of the story is going to be your a nice pure fermionic story, and part of the story is going to be a bosonic story. But you're going to have tensor them together, and you're going to be working with operators that that do something to the bosonic piece and something to the fermionic piece at the same time. Okay, so we'll get to that later, and so this is about. But for right now, you should think that in terms of the theory of differential forms, I'm just kind of looking at what's happening at a point and about how to manipulate those, the finite number of these wedge products at a point. That's all that's really going on for me now. And then this business of even versus odd is, do you have an even or an odd number of generators in your wedge product? And if you want to do calculations in differential forms, you have to keep track of, the fact that in your wedge product, if you interchange two things, you're going to pick up a minus sign, and that's all that's going on now. Does that help?
Yeah. Okay.
Okay. So, anything else? No? Okay. Okay. So I'll come back next time and try and finish this story, and then get on to the spinners. Okay. Bye now, and I'll be around for a while. Definitely come back and say hello, and if you want to talk about something else. Bye.
And